Now, the next what we are going to discuss in this module, that is module number 16, we are going to discuss about overall mass transfer coefficient. Just if you can recall what we have done in the previous class, where if I have XA and if you have YA, and this is the YAG concentration in the bulk of the gas and concentration in the bulk of the liquid is XAL, the interfacial concentration can be estimated if you know the mass transfer coefficient for the gas phase and the mass transfer coefficient for the liquid phase. This is going to become YAI and this is going to become XAI. But now the question is, one can estimate YAI and XAI using the relationship YAG minus YAI divided by XAL minus XAI minus KX by KY, and writing YI is equal to F into XAI. And as we know, if the solutions are dilute solutions, or maybe if the solutions are ideal solutions, maybe one can use the Raoult's law, maybe one can use the Henry's law, or maybe you can use the Raoult's law, and we can have some sort of a functional relationship. But if the solution is not ideal solution, and if the solution not obeys the Henry's law, then putting a simple functional relationship like this is not easy. This is a complex, there will be a complex functional relationship. That's what we can see. This equilibrium relation is highly nonlinear in nature. And at the same time, we also understand it is not that easy to estimate the mass transfer coefficient in the liquid phase as well as the mass transfer coefficient in the gas phase. So one can conclude that estimations of or the calculations of YAI and XAI from this equation is not so simple. Then what to do? Then what to do means we should in a position to have, like this is what we said, this is XAI, this is the YAI, this is the YAG, this is the XAL. So now what to do? We can use this relationship and we can do it, but the thing is the estimations is not that simple. This is the complex, this is the cumbersome process for the estimations of interfacial concentration. When we don't know the values of interfacial concentration, we cannot estimate Na is equal to Ky into Yaz minus Yai, or this is equal to Kx XAL XAI minus XAL. So we are not, it is not that simple to estimate the YAI or XAI. So one cannot estimate the flux value Na so simple. Then what to do? What we have to do, we have to measure the concentration. Measuring the concentration means you can take some sampling device, we can take the fluid in the bulk of the gas, and we can take the fluid in the bulk of the liquid. So we can get YAG value and we can get the XA value. And now you can take the same sampling device and try to take the concentration at the interface. And you see the thickness of the interface is very small. This is what we all seen when we are solving some problem using the film theory. We got the film thickness. Is in the terms of millimeters. The thickness, film thickness of this much. But now we are talking about the interface. The interface thickness is much more lower. So when the interface thickness is much more lower, any sampling device that we are going to take, when you want to take the fluid at the interface, we will not get the fluid at the interface. Maybe we will be getting, because the size of the needle, the diameter of the needle of the sampling device is bigger in diameter than the interface thickness. So when you want to take the sample at the interface, we will not get the fluid at the interface. Maybe we will get the fluid at this place, or we will get the fluid at this place. So if you take such type of fluid and if we can measure the concentration, we will get some concentrations, and these concentrations are not equal to YAI and XAI. When these concentrations are not equal to YAI and XAI, either you cannot use this equation or you cannot use this equation for the estimations of fluxes. So how to get rid of this problem, right? Are you understand or not? Any sampling device that we use for the sampling of the fluid at the interface is having a diameter which is bigger than the interface thickness. When the diameter is bigger than the interface thickness, then we cannot get a sample or we cannot get a fluid at exactly interface. So when we cannot get the fluid at the interface, whatever the concentration, those concentrations cannot be equal to your YAI and XAI. So we cannot estimate the flux. This is what I want to tell you. This is our beginning to talk about the overall mass transfer coefficient, and this is what similar to your overall mass transfer coefficient in the case of heat transfer process, where we are talking about overall heat transfer coefficient, because we have thermocouples and measuring of the temperature at exactly interface is not that easy compared to the mass transfer. In the case of heat transfer process, you may measure the little below or above the interface and we can get some values of the temperatures, but in the case of mass transfer operations, it is impossible to get the interfacial concentration. That is the reason we are going to talk about the overall mass transfer coefficient, or we may say local overall mass transfer coefficient. Why we are calling it the local overall mass transfer coefficient, that we will discuss at a later stage of a time. Now when you look at this, we have YAG. This YAG may be measured in terms of YAG, or we may measure in terms of XA star, right? We can say the concentration YAG, that concentration we say YAG, or we can say that is also equivalent with the XA concentration, XA star. XA star is the equilibrium concentration, or the concentration which is equilibrium with the given gas phase concentration in the bulk, and at the same time we have XAL, we can measure as XAL, or we can say YA star. So we can say the overall driving force is the YAG minus XAL, or we can say the overall driving force is YAG minus YA star, right? See, here we have a YAG concentration, we have XAL concentration. The overall driving force now is a YAG minus XAL, but the thing is XAL is having some functional relationship with YAG. We cannot simply write it as YAG minus XAL. So what we are trying to do, we are, instead of measuring XAL in terms of XAL, we can measure the XAL in terms of YA star. So what we can say, your YAG minus YA star can be written as YAG minus YAI plus YAI minus Y star, where this is the thing here plus this is the thing. Maybe what we are trying to do is YAG minus YA star is there, that is truncated into two terms, and from the definition you can see, maybe one can assume that this point and this point is in a very short distance. Maybe we can write this as a, maybe we can write it as a curve. Maybe for short distances we can write it as a straight line. We can write it as a straight line. So maybe I will erase it again and write it. So this is the curve. Maybe we can write it as a straight line with the slope of m prime, and similarly we can write this is the actual curve, and this can be written as another straight line with the slope of m double prime. So what I want to tell you, if the distance between this YA star and YAI are very short, maybe the curve can be represented as a straight line with the slope of m prime, and similarly if the distance between YAI and YAG is a very short, then or the difference in the concentration of interfacial concentration and bulk concentrations are very small, the equilibrium relationship can be represented as a straight line with the slope of m double prime, and here the equilibrium relationship can be represented as m prime. So here YAG minus YAI, this can be written as, right, m prime xai minus xal. As we know, overall coefficient, as I told you, for the solute transfer, how much of solute that is transferring from this phase to this phase, gas phase to the interface, the same amount of solute that is transferring from the interface to the liquid phase, or what we can say, this solute transfer is a constant value, and that is nothing but your Na also can be written as maybe overall driving force Ya Ky multiplied by Yag minus Ya star. So we can write it as now here Yag minus Ya star is there. So this can be written as Na by capital Ky, where capital Ky is called as the overall mass transfer coefficient. Yag minus Yai can be written as Na by small ky, that is the mass transfer coefficient in the gas phase, m prime into Na, that is Kx, mass transfer coefficient in the liquid phase. And when you cancel Na, it is going to become 1 by capital Ky, that is equal to 1 by small ky, m prime by small kx. That is ky is called as the overall mass transfer coefficient, and 1 by ky is called as the resistance, overall resistance. Here we call it as a small ky. This is nothing but a mass transfer coefficient for the gas phase, and 1 by ky we call it as a resistance offered by the gas phase. So kx is nothing but mass transfer coefficient for the liquid phase, and m prime by kx we call it as a resistance offered by the liquid phase. So your overall resistance is equal to resistance offered in the gas phase, plus resistance offered in the liquid phase. So there are two resistances. That is the reason we call it as a two-phase resistance theory or two resistance theory. So your overall coefficient, 1 by overall mass transfer coefficient is equal to 1 by mass transfer coefficient for the gas phase, m prime, where m prime is the Henry's law constant, divided by kx, where mass transfer coefficient for the liquid phase. Similarly, what one can prove, instead of using gas phase mass transfer coefficient, we can use the liquid phase mass transfer coefficient, and we have a liquid phase mass transfer coefficient of Xa star minus Xal, and that can be written as Xa star minus Xai plus Xai minus Xal. This is going to become Yag minus Yai divided by m double prime plus Xai minus Xal. This can be written as 1 by capital Kx, overall mass transfer coefficient for the liquid phase, based on the liquid phase concentrations, m 1 by kg m double prime plus 1 by small kx. This is the overall mass transfer coefficient based on the gas phase concentration. This is the overall mass transfer coefficient based on the liquid phase mass transfer coefficient. So 1 by capital X is equal to 1 by small ky into m double prime, where m double prime is the Henry's law constant between the values of Yai and Yag. And 1 by kx is the mass transfer coefficient for the liquid phase. So this is based on the gas phase concentration. This is based on the liquid phase concentrations. And your overall resistance is nothing but 1 by mass transfer coefficient. That is nothing but a resistance offered in the gas phase plus resistance offered in the liquid phase. Now, so if I can independently estimate the ky value and kx value, if I know the m prime value, I can estimate my ky value. So once if ky value is known, I can use my Na, that flux is equal to ky, capital Ky into Yag minus Yai, Ya star, and that can be used for the calculations of the fluxes. Now, so we can say resistance in the gas phase. Sometimes what in the most of the people what they say, 60% of the resistance is in the gas phase. That means resistance in the gas phase divided by overall resistance is equal, let's say, 60%. That means 1 by small ky by 1 by capital Ky is equal to 60%. So maybe if one can say if small ky is estimated, and if you say it is 60%, capital Ky can be estimated. Once if you know the capital Ky, one can estimate the flux. So similarly, resistance in the liquid phase by total resistance also can be calculated. So now we can have some special cases. Suppose if you say membrane is very small, that is very flat. When you say equilibrium diagram is very flat, or what we can say, a small changes in the concentration produces a large concentration changes in the liquid phase, or what we can say, small concentration changes in the gas phase produces large concentration changes in the liquid phase. So that means your membrane is going to become very small. That is happening when you are talking about a system like ammonia, maybe HCl, maybe where the solute is having a high solubility in the liquid phase, high solubility in the liquid phase, or maybe high solubility in the water. So your membrane is going to become very, very small. So when membrane is going to become very small, membrane by Kx is going to become very small. Membrane by Kx is equal to very small. So your 1 by capital Ky is almost approximately equal to small ky. 1 by capital Ky is approximately equal to 1 by small ky. That means the total resistance is controlled only by the gas phase. And what we call it as a gas phase controlled. This type of things we call it as a gas phase controlled. Your gas phase is controlling the overall resistance. Your gas phase is controlling the overall resistance. Try to understand. Initially we started with the 3 resistances, and what we said is interfacial resistance is negligible, and we have only the 2 resistances. Now what we say, for highly sparing, highly soluble gases, highly soluble solutes in the liquids, the membrane value will be very, very small. If membrane value is very, very small, membrane by Kx is going to become much more smaller, very, very smaller. So when it is going to become membrane by Kx is equal to very small. So 1 by this of this, 1 by membrane by Kx will be very, very small. So what one can say, 1 by capital Ky is approximately equal to 1 by small ky. So this is what we call it as a gas phase control, and that is the case for the systems like a water, NH3 in water, maybe HCl in water. If such type of cases, we call it as a gas phase control. Here, suppose if you want to reduce the total resistance, as we discussed, either you can reduce the liquid phase resistance or the gas phase resistance. When gas phase is controlling the overall resistance, there is no point of decreasing the resistance of liquid phase. How to decrease the resistance of the liquid phase? By increasing the turbulence. When you are going to increase the turbulence, the mass transfer coefficient for the liquid phase is going to be increasing. When the mass transfer coefficient for the liquid phase is going to be increasing, so the overall resistance is going to be decreasing. But even large changes in the mass transfer coefficient for the liquid phase will not changes much in the overall mass transfer coefficient. So there is no point of sending the fluid with liquid with a high velocity. So there is no point of changing, altering the values of Kx. Instead of that, what one can do, it is better to reduce the resistance in the gas phase. How to reduce the resistance in the gas phase? We have to increase the mass transfer coefficient for the gas phase. How to increase the mass transfer coefficient for the gas phase? We have to increase the turbulence, or you have to increase the flow rate of the gas phase. When you are going to increase the flow rate of the gas phase, your Reynolds number is going to be increasing, your turbulence is going to be increasing, your mass transfer coefficient for the gas phase is going to be increasing, and that will have a more influence on the overall mass transfer coefficient. So when you talk about the gas phase control systems, there is no point of increasing the mass transfer coefficient for the liquid phase when we want to reduce the overall resistance. Then the second thing is, when you talk about the another case, MW prime is very large. MW prime is very large. MW prime is very large means, and that means a small changes in the liquid phase produces the large changes in the gas phase. If small changes in the liquid phase produces the large changes in the gas phase, your MW prime will be very, very large. If the MW prime is very large, 1 by kg into MW prime is a very small when compared with the 1 by kx. So if that is the case, what one can say, a capital Kx is approximately equal to 1 by small kx, and this is what we call it as a liquid phase controlled. We call it as a liquid phase controlled. if this is the case, for example, when you talk about high viscous liquids, when you contact with the gases where the gases is having high solubility for the solute, so the resistance offered by the gas phase is so negligible compared to the resistance offered by the liquid phase. If that is the case, we call it as the liquid phase controlled. When it is the liquid phase controlled, 1 by capital Kx is approximately equal to 1 by small kx. Now, if this is the case, if you want to increase the, if you want to reduce the overall resistance, there is no if you want to reduce the overall resistance, it is better to reduce the resistance in the liquid phase rather than changing the gas phase resistance, because gas phase resistance will not have a much influence on the overall resistance. Gas phase resistance is not having much influence on the overall resistance. So if that is the case, what one can do, we can increase the liquid phase mass transfer coefficients by increasing the flow rate of the liquid. So once if the flow rate of the liquid is increased, Reynolds number is increased. Once Reynolds number is increased, the turbulence is increased, the mass transfer coefficient for the liquid phase is increased. Once the mass transfer coefficient for the liquid phase is increased, overall mass transfer coefficient is going to be increased. Overall mass transfer coefficient is increased, the flux is going to be increased. So what I want to tell you, there are two special cases that we are going to come across. One we call it as a gas phase controlled, other one we call it as a liquid phase controlled. And some systems like we may have a systems like HCl, maybe dissolution of CO2, maybe SO2, maybe oxygen. When you want to transfer either CO2 or SO2 or oxygen from the gas phase to the liquid phase, both the resistances are important, because the CO2 or SO2 or oxygen doesn't have a much solubility, high solubility in the liquid phase. So the liquid phase resistance is important as well as the gas phase resistance is important, and your overall resistance is equal to resistance in the gas phase plus resistance in the liquid phase. So what one can do, so either you can change the Reynolds number of the gas phase, or you can change the Reynolds number of the liquid phase to change your overall resistance. And now, and these are the some special cases what we are discussing, and what we say, your overall resistance is equal to sum of the two resistances, and it depends on the what we discussed. We discussed about some special cases where we said is a gas phase controlled and a liquid phase controlled. I'm sure you understood what I'm talking about it. Then we have taken, in this case, we have taken a problem of absorption, that is a system of ammonia, air and water system, and we have discussed the estimations of your overall mass transfer coefficient for the absorption problem. But in mass transfer operations, it is not an absorption problem. We may come across any sort of a problem, and in general what one can say, if one phase is the E phase, other phase is the R phase. We said gas phase and the liquid phase, but in some cases we may not come across the gas phase, we may not come across the liquid phase. If that is the case, we call it one phase as the E phase, other phase we call it as the R phase. And the concentration of a solute in the R phase, we can say J. The concentration of solute in the E phase, we can call it as a I, right? And if that is the case, 1 by capital Ke is equal to 1 by small ke plus m prime by small kr. This is overall resistance based on the gas phase concentration. I mean overall resistance based on the E phase concentrations, or we may say 1 by capital Kr is equal to 1 by small kr plus multiplied by mw prime 1 by small ke mw prime 1 by small kr. So this is the overall resistance based on the R phase concentration. This is the estimations of overall resistance based on the E phase concentrations, and your m prime is equal to IAI minus IA star divided by JAI minus JAR, and MW prime is equal to IAE minus IAI divided by JA star minus JAI. So these are the equations that are used for the estimations of M prime and M double prime. So that is what I told you. The problem whatever we have discussed till now, it is applicable for the gas phase and liquid phase. But any phases that we come across, one phase we can call it as a E phase, where the concentration is representative of I. We can call it as another phase is a R, and where the concentrations are going to be called as a J, and then this is the equation that we are going to get it. But you should not be too much of confused with this, and what are the previous equations that we derived, the same equations are going to be applicable. Instead of gas phase, we can say solid phase. Instead of liquid phase, you can say gas phase. So we have a solid and gas phase. So anyway, whatever the way you want to remember, that way you can remember. Then sometimes this K values is a special cases, as you know. Either it may be applicable for the equimolar counter diffusion or non-diffusing. We are going to come across a general coefficient. If a system is not comes under the either equimolar counter diffusion or not comes under the non-diffusing B, then we have to use the general coefficients. Those general coefficients we call it as a F coefficients. And if these F coefficients are there, your Na is equal to Na by sigma Na, sigma n, Fg ln of Na by sigma n minus Yai divided by Na by sigma n minus Yag, that is equal to Na by sigma n Fl ln of Na by sigma n Xal divided by Nai minus sigma n Xai. So this is the thing that we can use, and where n is equal to n, sigma n is equal to Na plus Nb plus Nc, and maybe your stoichiometric equations or maybe other things that will help us to know the flux of individual components. Then we can calculate the overall flux. Then we can calculate the flux for individual component. So what we can have some sort of a iterative method that we have to use, or maybe iterative methods that you have to use to solve the expression, or maybe we can say Na by sigma n Yai, Na by sigma n Yag is equal to Na by sigma n Xal, Na by sigma n Xai to the power of Fl by Fg, Fl by Fg. So what we have to do, we have to know mass transfer coefficient for the liquid phase, mass transfer coefficient for the gas phase, and we have to know interfacial concentration. It is not that easy to calculate the concentrations Yai and Xai as compared to the previous one. In this case, what one can do, so we can Yai and Xai can be replaced as Ya and Xa, and if you know the mass transfer coefficient for the liquid phase, mass transfer coefficient for the gas phase, and Na by sigma n is known to you, then one can calculate the Ya and Xa. Once if you know the Ya and Xa, maybe that point we can substitute. Then again we have to solve the simultaneous equations to solve this sort of a problem, and the problem is little cumbersome. Then we are going to come across this is the way one is going to be solved for a general problem. Then sometimes what is happening, we have developed the correlations assuming that there is a flow in the gas phase, there is a flow in the liquid phase, and we have assumed that, and this gas phase and the liquid phase are flowing in the same vessel, and what will happen, the turbulence in the liquid phase may influence the turbulence in the gas phase, or vice versa. The turbulence in the gas phase may influences the turbulence in the liquid phase. So whatever the Reynolds number that we have used, whatever the flow rate that we are using the gas phase, that may be changed because of influence of the liquid phase on the gas phase. So we have to take the actual Reynolds number for the estimations of mass transfer coefficient for the gas phase. Similarly, we have to take the actual mass transfer coefficient for the estimations of the liquid phase. Sometimes what will happen, so when we have a ethyl ether, we have a ethyl ether which is transferring from the water, like maybe I have a water, maybe I have a ethyl ether, and this water and ethyl ether, we have a interface, and here we have a air. So when ethyl ether is passing or transferring from water phase to the air phase, what will happen? There may be lot of turbulence at the interface. When there is a lot of turbulence at the interface, maybe it is providing so much of swirling and other things at the interface, it will provide a lot of turbulence at the interface. So now the concentrations or the flow, the turbulence at the interface will be different from the turbulence in the liquid phase as well as the gas phase. Because of that, your overall mass transfer coefficient is going to be, your mass transfer coefficient at the interface will be more compared to the mass transfer coefficient calculated either based on the liquid phase concentration and liquid phase, or based on the calculations in the gas phase. So what I want to tell you, when certain substances are transferring from one phase to the other phase, at the interface some sort of a thing is happening where so much of turbulence is going to be increased, so much of turbulence is going to be created. Because of this turbulence, your mass transfer coefficient is going to be increasing. In some cases what will happen, a reverse phenomena is going to be occurs. So when a surfactant molecule, as I told you previously, acetyl alcohol is transferring from water phase to the air phase, the interface is going to form, the interface is so rigid interface. And when the interface is so rigid, the three things which are going to happen, one is the solute molecules block this interface, may block the solute transfer. Then the second thing, what is happening, makes the interfacial layer so rigid. Then a third thing that is going to occurs, interact with the transferring solute, interacting with the transferring solute. So what I want to tell you, in the case of ethyl ether, when it is transferring from the water phase to the air phase, the ethyl ether, when it reaches to the interface, it creates so much of turbulence at the interface. Because of this, the overall mass transfer coefficient at the interface is going to be increasing, and because of that, the mass flux is going to be increasing. But when you talk about certain type of particles, and this is called as the Marangoni effect. Marangoni effect. And in some cases, what will happen? So if either water or the either gas phase or the liquid phase contains some surfactant molecule, and it will be forming a rigid layer at the interface, and because of that, the interface may block the solute transfer, makes the interfacial layer is so rigid and interacting with the transferring solute. Because of that, your mass transfer coefficient is going to be decreasing and your overall flux is going to be decreasing. So this is what we call it as a Marangoni effect. Now we said it is a local overall mass transfer coefficient. Now we call it as a average overall mass transfer coefficient. Why we are calling as a average overall mass transfer coefficient? Why we are calling as average overall mass transfer coefficient? Suppose if you are going to take a wetted well column, maybe a tray tower, wetted well column. So we have a gas phase and we have a liquid phase. So what is happening here? Gas phase is going up, the liquid phase is flowing down. So here the concentration of solute in gas phase is high, and here because some solute has transferred from the gas phase to the liquid phase, solute concentration is less. Solute concentration is less, or other way what we can say, the concentration of a solute is changing from bottom to the top. When the solute concentration is changing from bottom to the top, your driving force is going to changes. Once the driving force is going to changes, your mass transfer coefficient is going to changes. So what one can say, your mass transfer coefficient, whatever we said in the previously, that is the mass transfer coefficient at a particular location, and we have infinite number of such type of locations. So what one can do, we can take a mass transfer coefficient location 1, mass transfer coefficient at location 2, maybe infinite number of points that we can take, and we can find out the overall mass transfer coefficient for the design purpose. But if the concentration changes are not much, and when the concentration changes are not much, what one can do, we can take the mass transfer coefficient at the bottom, we can take the mass transfer coefficient at the top, and we can take the average of these two values, and that is what we call it as the average overall mass transfer coefficient. And now what is happening here, so your embrime is going to changes because your equilibrium distribution diagram is going to changes, your kx and ky are going to changes, and maybe this value is changing and this value is changing, and this value divided by this value may be a constant value. If that is the case, your overall coefficient is not going to vary much. If the overall coefficient is not going to vary much, instead of taking about the local mass transfer coefficient, we can call it as a average overall mass transfer coefficient. So what we have studied in this class, if you recall, as we said, it is not easy to estimate the concentration at the interface. So instead of using individual mass transfer coefficients and driving force in the each phase, what we can do, we can use the overall resistance for the estimations of the fluxes, and that is what we have learned today. And in the next class we will discuss about different types of contacting devices, different types of contacting patterns, maybe co-current operation, maybe a counter current operation, and we can discuss something like how to devise the operating line equation, what is the meaning of the equilibrium diagram. All those things we are going to discuss in the next class. Thank you very much.